Hello, I'm Dr. Maurice Dupre, and in this section we're going to discuss fluid pressures and forces. The problem of computing forces, for instance, on vertical plates and windows in aquariums, things which are subject to the pressure of a fluid, is complicated by the fact that pressure varies with depth in a fluid. Let's look at the exact relationships. We begin with the pressure-depth equation. In a fluid that is standing still, the pressure P at depth h is the fluid's weight density W times h. In other words, the pressure is simply W times the depth h. Now, keep in mind that's the distance from the surface down to the depth where you are, where you're measuring the pressure. So in order to figure out the pressure, then you have to know the weight density of the fluid. A couple of good things to keep in mind for many physical problems is fresh water has a weight density W equal to 62.4 pounds per cubic foot. Seawater has a weight density of 64.0 pounds per cubic foot. Notice seawater weighs more than fresh water. That's because of the dissolved minerals and salts in the seawater. This means that a given object will have a greater buoyant force on it in seawater than in fresh water. For instance, keep in mind that if I have a region of fresh water, since we're assuming the fluid is still, if I take any region, for instance, just think about this for a second because it's a useful mental exercise. You've got a fluid here. Let's think of it as being in a tank. And suppose I consider any region blob of stuff in the tank. It's a three-dimensional blob here. Now, if the fluid is still, that blob is not in motion. On the other hand, the volume of that blob multiplied by the weight density is the downward force that gravity exerts on the blob. And so consequently, the fluid itself outside that blob must be exerting an upward buoyant force that's counteracting that downward weight of the blob. And so consequently, when you consider any region of the fluid, any solid region, the buoyant force upward is in effect related to the weight density times the volume of the region. And so the greater the weight density, the greater the buoyant force. Well, let's look at how we use the relationship between force and pressure in this situation. Remember, the force on a surface due to pressure is simply the pressure times the area of the surface. That is, if we've got a fluid here on, for instance, think of this surface here as being perpendicular to the plane of the paper, sort of a perspective of it. We're kind of looking at it slightly from an angle at the front, and we've got fluid to the left of that surface, so it's pushing on it. Well, that surface has an area A, and the force that results from that pressure is perpendicular to the plane of the surface, and it's given by the formula force equals pressure times area. In effect, if the pressure is constant throughout the surface, we could measure the force on the surface, and measuring the force, measure the area, divide the force by the area, and that by definition gives the pressure. So force is pressure times area. On the other hand, we know in a fluid the pressure at depth h is W times h. So if the surface in effect has constant depth, in other words, if it in fact has virtually no appreciable height and is just a long vertical horizontal strip, then this equation that pressure is W times height would apply virtually throughout that strip if the height is very tiny. And so that allows us to calculate the force on a narrow horizontal strip sitting in the fluid. Okay, so now if we want to calculate the actual force on a full vertical plate immersed in the fluid, look at this picture. I've got a vertical axis here, I'll call it the y-axis, and here's some plate. It's got some shape, and think of it as vertical, and we're looking at it face on. Here, little wiggly lines, the surface of the fluid, little waves on top, which have no appreciable effect. We'll think of them essentially wave height is 0. Now, if I look at the horizontal strip here, part of this flat plate, which has length L of y, all that capital L of y, then the area of that little strip, dA, is L of y dy, a little bit of vertical variation there, dy. And so consequently, the pressure force on that is simply the strip depth. Well, that's the distance from this level y up to the surface, which you'd have to compute in terms of your vertical coordinates, times the L of y dy times the weight density of the fluid. And so to calculate the total force on this, you would integrate from the lowest part of the flat plate in the fluid, A, up to the surface, if the surface is below the top of the plate, or if the plate is totally immersed, you would just integrate to the top of the plate. So that's the method of calculating forces on submerged plates. Now let's compute the fluid force on the window of an aquarium tank where the tank is full of seawater. New England Aquarium. The viewing portion of the rectangular glass window in a typical fish tank at the New England Aquarium in Boston is 63 inches wide and runs from 0.5 inches below the water's surface to 33.5 inches below the surface. Find the fluid force against this portion of the window. That is the whole window under the surface, in effect. Okay, let's look at a picture. It's best to draw a picture when you're working these kind of problems. So here I've drawn crudely the surface of the fluid, see little waves, and here's the rectangular window, not drawn to scale, but it's 63 inches wide, and if the bottom is 33.5 inches below the surface and the top is just a ½ inch below the surface, then the window itself is obviously 33 inches high. Now remember, the weight density of seawater is 64 pounds per cubic foot, but all our dimensions are in inches, and a cubic foot is 12 cubed. That's a very big number of cubic inches. So if I convert all these units back into feet, I'm going to have a lot of fractions. It's better to go the other way. Let's just convert our density from pounds per cubic foot to pounds per cubic inch. Well, to do that, we just divide the 64 by the 12 cubed. So I'll write W sub inch for the weight density of seawater in pounds per cubic inch. So that's 64 divided by 12 cubed pounds per cubic inch. And so now let's compute the force. Well, let's look at our picture again just briefly. Now notice, for a given strip at height y from the bottom of the window, the length across L of y is 63 inches. And so consequently, the length of our strip L of y is constant. But what's the depth of this strip? Well, if it's y inches from the bottom and it's 33.5 inches from the bottom to the top, then the depth is 33.5 minus y. So we're going to have our weight in seawater times the 33.5 minus y multiplied by the width L of y 63, and of course times the little bit of depth dy. And so that's our little bit of force on that little horizontal strip of width dy. And so the total force would be the definite integral from the bottom of the window, that's at y equals 0, up at the top, where y equals 33, of the W sub inch, that's the weight of seawater in pounds per cubic inch, the weight density, times the 33.5 minus y times 63 dy. And of course we can pull this constant out and we can pull the 63 out, and so out front of the integral we have 64 times 63 over 12 cubed, and multiplying by the definite integral from 0 to 33 of 33.5 minus y dy. So that's our force, and there's what we have to compute. So let's begin the computation. We just begin by anti-differentiating here. The antiderivative of 33.5 is 33.5y when we anti-differentiate with respect to y. So our force, F, is equal to 64 times 63 divided by 12 cubed, 33.5y minus the antiderivative of y, which is y squared over 2, and that's to be evaluated between limits 0 and 33. Well, obviously putting in 0 gives us nothing, so I just have to put in the 33. So the force here is simply 64 times 63 divided by 12 cubed times, when I put the 33 in, let's write this 33 as 0.5 as 33 plus a half multiplied by 33 minus 1/2 33 squared. So when I look at this, notice what I'm going to get. 33 times 33 is 33 squared minus a half 33 squared. That contributes simply 1/2 33 squared, and this other term is a half of 33. So in effect, what I get is the force is 64 times 63 divided by 12 cubed. We can take the 1/2 out, times the quantity, 33 squared plus 33. And so all we have to do is simply compute that, and that's easy to do. It comes out to 1,309 pounds. Now remember, our units for the length here, the inches, in effect cancel out completely in the end in this problem, and so our units of force come out in pounds. Now let's look at an example where we compute the force on a submerged plate and where the shape of the plate is not simply rectangular. Semicircular plate. A semicircular plate 2 feet in diameter sticks straight down into fresh water with the diameter along the surface. Find the force exerted by the water on one side of the plate. Now keep in mind, when you submerge a plate like this into water, there is no net force on the plate. The water on one side pushes with the exact same force as the water on the other side, so they exactly balance each other. On the other hand, we know since the plate has a diameter of 2 feet, the radius is simply 1 foot. Now, you'll notice that when we do these problems, if we use the surface of the water, for instance, as depth 0 and have our axis going upwards, then we typically end up dealing with what we really need is the distance here minus another thing, and we end up with a difference and introduce several constants in here. In order to simplify, here's a little trick that you might note. What I've done is to take the y-axis pointing down. When I do that, taking 0 right at the surface, then my y-coordinate becomes the depth exactly, and so that will simplify things considerably. Okay, in effect, what that means is we can turn the whole plate right side up, and having it sitting on top of this horizontal line, which we'll think of as the x-axis, y is still the depth. And so here's what the picture looks like. When I put it this way, here's the horizontal strip at height y, which is depth y. And so we recognize that semicircle has equation y equals square root 1 minus x squared, because it's a semicircle of radius 1 centered at the origin. So that means x squared plus y squared equals 1 along this surface, and so I can solve for x. So notice x, with this being y right here, this x is only half of the length of the strip across, and clearly x is the square root of 1 minus y squared. So the length of the horizontal strip at height y is 2x, which is 2 times the square root of 1 minus y squared. So that means our little bit of force on that horizontal strip is the weight density of fresh water, 62.4, times the depth y, times the area of the little horizontal strip, which is twice the square root of 1 minus y squared times this little bit of vertical thickness, which is dy. Now, how far do we integrate? Well, we're going to be integrating from the surface all the way down to the radius of the plate, which is 1. So we're integrating y from 0 to 1. So that means our force integral is the integral from 0 to 1, 62.4, 2 times y square root 1 minus y squared dy. So we'll take out the constants. The force is therefore 62.4 times 2 times the definite integral from 0 to 1 of y times the square root of 1 minus y squared dy. Now, of course, when you see radicals like that, you know you have a little bit of trouble, but in this case, because of the factor y outside the radical, we see right away it's an easy candidate for substitution. We just substitute u equals 1 minus y squared. Then, of course, du is negative 2y dy. Here's our y. Well, here's a 2. Let's just pull it back inside the integral. And so if I pull this 2 back in, then 2y dy, all we need is the negative sign. So force then becomes the negative 62.4. The 2 has gone into the du, integral square root u du. But we have to replace our limits now with limits in terms of u. When y is 0, u is 1. And when y is 1, u is 0. Notice our upper limit is actually smaller than our lower limit. Since we have a negative sign here, we can get rid of the negative sign by switching the limits. So this would be 62.4 times the definite integral from 0 to 1 of u to the 1/2 power du. Well, that one's pretty easy to do. Antiderivative of u to the 1/2 is u to the 3/2. So we have 62.4 definite integral from 0 to 1, u to the 1/2 du equals 62.4 times u to the 3/2 divided by 3/2 to be evaluated from 0 to 1. That's a 3 there. Well, in any case, that's easy to do because u to the 3/2 evaluated at 1 is simply 1, and evaluating at 0 gives 0. And dividing by 3/2 is the same as multiplying by 2/3. So we end up with 2/3 times 62.4, which is 124.8 thirds, or 41.6. And what's our units here? Pounds. Remember our weight density for the fresh water was 62.4 pounds per cubic feet. Our distance measurements were in feet, and so consequently our units of force are in pounds. Now let's look at a problem where we calculate the force on a plate in a tank that has some variable water level in it, and one of the sides of the tank is held in place by a spring. This complicates things considerably. Here's the picture you should keep in mind. Notice here I have a tank that has a semicircular cross section. At this end, the tank has water in it. We'll assume this is fresh water. And notice the water is held in place by, on one end, a movable plate. The reason this end is movable is because it's held in place by a spring, and of course the depth of the water determines how much force is on this plate, and so consequently how high the water is will determine the position of the plate. And notice what there is right here, a drain hole. So suppose we start pouring water into the tank. As we fill the tank, the force on this plate increases, and naturally that pushes the plate back. So here's the question. Will the tank overflow, or will the force on the plate as the water rises be large enough to push the plate back over the drain hole so that the drain hole will protect the tank from overflowing? Here's a side view. Notice there's a 5-foot distance from the place where the plate is to start here. There's water in the tank. And so the question is, will this water in the tank push the plate back 5 feet and allow it to drain out? And of course, with water pouring in, the level's going to keep getting higher. The force on that plate keeps getting greater, pushing it back. Will it push it back far enough? We'll assume that the spring constant K is 100 pounds per foot. So let's look at our problem. Water pours into the tank here at the rate of 4 cubic feet per minute. The tank's cross sections are 4-foot diameter semicircles. One end of the tank is movable, but moving it to increase the volume compresses the spring. The spring constant is K equal 100 pounds per foot. If the end of the tank moves 5 feet against the spring, the water will drain out of a safety hole in the bottom at the rate of 5 cubic feet per minute. Will the movable end reach the hole before the tank overflows? Notice we're told water is going in at 4 cubic feet per minute, and since it will drain out at 5 cubic feet per minute once the safety hole is exposed, that means we'll have a net outflow of 1 cubic foot per minute, and the tank will start draining and the level will go down, keeping it from overflowing if that safety hole is ever passed by the movable plate. So let's look at the picture again. Here's our situation. Notice if I have the y-axis going up, and I'll take y equals 0 right here at the top of the plate, so there's the x-axis going along the top of the plate. Since the diameter of the tank is 4 feet, the semicircle here has diameter 4 feet, so its radius is 2. And so consequently, the equation of a circle centered at the origin here is x squared plus y squared equal 2 squared, which is again 4. This maximum depth then is 2. Here's the drain hole. Our spring constant K is 100 pounds per foot. And remember, Hooke's law is force equals constant times x, where x is the displacement. Of course, our displacement is the amount we move in this direction. Now, notice what we're going to have to compute. When the depth is at height h, we can calculate the force on the plate, and then using this equation, figure out what the displacement of the plate will be when the depth of the water is h. Now, one thing I'm going to do to simplify this problem is to turn the y-axis upside down. That will put the plate right side up, and it puts it into the position that I'm used to looking at when I'm dealing with semicircles. So turn the y-axis upside down. We're looking at a semicircle up here. Radius equals 2 feet, and remember, depth is now going up. Here, I've shown the cross-section picture. We'll assume the level of the water is h. Here's our typical horizontal strip at height y. And so notice, what's the depth of that strip? Well, it's that distance minus the distance from 0 up to the water level. Y minus h is the depth here at y. Now, what's the length of the horizontal strip here? Well, notice the equation is x squared plus y squared equal 4. So the length there across here is x from here to here, x equal square root of 4 minus y squared. And so consequently, the length at y is twice x, twice the square root of 4 minus y squared. So when the depth is h, the force, the little bit of force on that horizontal strip is the weight density of fresh water W times the y minus h twice the square root of 4 minus y squared dy. So there we have it. And so what do we want to integrate from here? What are our limits? Well, we're going from y equals h up to depth y equals 2. So what I've called F subscript h is the force on the plate when the depth is h. And so it's given as the integral from h to 2, w times the quantity y minus h, 2 times the square root of 4 minus y squared dy. Of course, we can take out the 2w and break this up into two terms. Notice the first term is just y times the radical, and the second term, negative, the constants that come out now are 2h and w. So negative 2wh times the integral h up to 2 square root 4 minus y squared dy. Now you'll notice that we can easily work out this integral by substitution, but this integral is going to be nasty. And so that will give us a nasty expression involving h. And here we want to solve the equation f sub h equals kx to get x in terms of h. And then, you could use the rate at which water is flowing in to calculate the displacement at time t, and then see if the tank ever overflows. Now this would be a real nasty problem to do, and so what we can really do is a vast simplification. And let's reason in this way. Notice that if the full tank will push the spring back to the drain hole, then it's possible that it would stop overflowing. On the other hand, if when the tank is full, it doesn't even push the spring back enough to expose the drain hole, then it's going to overflow. So as a simplification, let's begin by simply calculating the force when the tank is full. That would be in the case where the depth h is 0. So remember, h is the distance from the x-axis down to the top of the water level. That would knock out this entire term because h is 0 and also simplify this integral. So that's going to be our strategy instead. So let's calculate then the force on the full tank. That's where h equals 0. The force on the full tank is the definite integral from 0 to 2 wy 2 times the square root of 4 minus y squared dy, which is, of course, using 62.4 for the weight density of fresh water, times 2 definite integral 0 to 2 y times the square root of 4 minus y squared dy. Now, of course, this integral is an easy substitution. We'll just substitute u equals 4 minus y squared. So then du is negative 2y dy. We have a 2 here, so we'll just put it back inside. And we need a negative sign out front to compensate that. So we'll have negative 62.4 multiplied by the integral of this y, this 2, the dy gets absorbed into du, and this just becomes square root u, or u to the 1/2 du. What are our limits in terms of u? When y is 0, u is 4, and when y is 2, 2 squared is 4, 4 minus 4 is 0. And I like to switch my limits when I have a negative sign there. It just makes it easier to keep track of signs when I end up doing the evaluation between the limits and the end. So this is definite integral 0 to 4, 62.4 u to the 1/2 du, which is pretty easy to do. So now finally we have the force on the full tank. F sub full is equal to 62.4 times the definite integral from 0 to 4 of u to the 1/2 du, which is easy to do. The antiderivative of u to the 1/2 is simply u to the 3/2 divided by 3/2, and that's to be evaluated between limits 0 and 4. Of course, the lower limit 0 contributes nothing. 3/2 down here in the denominator becomes a factor of 2/3. So we have 62.4 times 2/3 times, substitute 4 in for u, that's 4 raised to the 3/2 power. Well, 4 to the 3/2 means the square root of 4 cubed, and the square root of 4 is 2. So we have 62.4 times 2/3 times 2 cubed. 8 times 2 is 16, so that's 16/3 times the weight density of fresh water, 62.4. And so this is the force in pounds on the plate. Now if we calculate that, what we find is it's 332.8 pounds. But remember, the force from the full tank gives a displacement to the movable end determined by Hooke's law. The full force equals kx, where k is the spring constant, and remember the spring constant was 100. And so that means the amount that the full tank displaces the movable end is the full force divided by the 100. Well, if I divide 332.8 by 100, I get simply x equals 3.328 feet. Do you remember how far that movable end had to go to reach the drain hole? 5 feet. So the full tank can only displace the movable end by 3.328 feet, and consequently the full tank will never even cause the movable end to reach the drain hole. That means the tank's going to start overflowing because water keeps coming in at the rate of 4 cubic feet per minute. Now, notice that in this problem, the 4 cubic feet per minute at which water is coming in and the 5 cubic feet per minute at which the water drains out are sort of like red herrings. Those numbers never entered this calculation. The only way they enter is to notice that the drain rate, 5 cubic feet per minute, is larger than the rate water is going in, so that you know that if the movable end reaches the drain hole, it won't overflow. Other than that, those numbers play no role here. All right, we've worked some problems computing forces on submerged plates. Remember, pressure is the important aspect of this problem, and pressure varies with depth.